In those situations where Newtonian gravity is correct, which we call the Newtonian regime, so for small masses like the Earth and for slow speeds like we're used to for non-relativistic things where Newtonian gravity gives exactly correct estimates, you can predict the eclipse, centuries in advance and so on. And a measure of the straightest lines, of the timelines, right? Although they're kind of like straight lines, this axis is like a straight line, really. It's kind of inertial, but it's not. The world lines have some kind of curvature, and that curvature in that complicated differential geometry theory of space-time curvature will have the same amount of curvature we would expect as the worldline curvature, which is the acceleration. In other words, if the acceleration is gm over r squared, which means that the worldline curvature is gm over r squared, we have a right to expect that in situations where Newtonian gravity is correct, which we call the Newtonian regime, this other theory, which is much more complicated and has many more things, will reduce to something which gives the same number. If it doesn't give the same number, it's wrong, right? It has to give the same number. If it gives the same number, we'll assume that it has the same functional form. When you have two things that give the same number over a certain range for things, projectiles and so on, they're going to have the same functional form. So we have every right to expect that that measure of the curvature of these lines of the straightest lines in this curved spacetime will look the same. In other words, it'll be like gm over r squared. It'll look the same as the curved lines. So what you have really is two perspectives. You have a curved spacetime, and then you have the perspective of people who don't realize that you have this curved spacetime, or call it time warping within the context of spacetime. And they're drawing a time axis straight like this, a space axis like this, because they don't realize that time is warped. When they do that, they're going to see inertial particles and think that they're accelerating. We are not in an inertial frame. We are accelerating. So we cannot say that we see something falling, it has a curved world line, because we have curved world lines. We're not capable of judging what has an inertial world line. So from that perspective, we draw a straight t-axis and an x-axis, and we draw these accelerated particles as though they're a curved world line, where they don't. They actually have a straight world line. But a straight world line as seen from the correct context of this warped time. And the curvature of the straightest lines in this curved spacetime, which we expect to be similar functionally to the curvature of these world lines, right? I want to do one other feature of this model. Okay, here we get a little bit kind of into differential geometry, but not really. It's not going to be quantitative. We're going to claim that these world lines, these gravitational freefall world lines, are actually inertial, meaning that they're straight lines. Is there any property that we can observe within our illusion of flat spacetime that ascribes really geodesicity, straightness, to these curved world lines, freefall world lines? And the answer is yes. There are certain things that we can tell. For example, when you're in freefall, if you have these particles crisscrossing, right? What will they see if they're all moving past each other at this region where they're just almost just missing each other, different speeds and so on and so forth. They all have, one is, let's say, orbiting, that's in free fall. One has been thrown by a projectile and is going up and down like that. Another one has been shot straight like that, right? They all have different trajectories, different speeds, different angles. They just about meet at one point. Because they're all in free fall, they will not feel any accelerations. As far as they're concerned, therefore, they're all moving in a straight line, and in fact, they will all see each other moving in a straight line. If you imagine this as a thought experiment, you're jumping off a cliff, you know, before you pull the parachute, and there's a bullet going this way, and there's an astronaut, whatever it is, you will all see each other moving in straight lines for that instant as you cross paths. Because none of you are accelerating. Even the trajectory seems straight. Okay, and that's kind of an exercise, thought exercise to do at home. On the ground, you will see, everyone will see the other one as being, you know, accelerated with curved trajectories. Okay? At every moment as you're falling, you feel that you're inertial, which means that you have a straight line. And yet, the sum total of your line is curved, right? In other words, I'm in radio contact with this person who's falling down, and I say, okay, what are you, inertial? Etc. says, I'm inertial, I feel no forces on me, I'm inertial. So therefore, my world line should be straight. And then I ask him a second later, same thing, same thing, same thing. So he's constantly saying his world line should be straight. Yet I plot his world line, I mean, I see he has acceleration, I give it as curved. And in fact, since at every moment his world line is inertial, so we have like a paradox. He claims his world line should be straight, and at every instant it's straight, and yet overall it adds up to curved. How could that be? So the answer is that could be in a curved space. For example, take any curved surface, however it's curved. All right? It turns out that any curved surface can have defined on it a geodesic, something that is the straightest line. Straightness can be defined not only in a flat surface and in a flat space, but also on a curved surface. In every given direction, you start out like this, there's a unique continuation of that that would be the straightest possible. How do you do that? You kind of draw a little tiny straight line, then take another straight line next to it, move it up along it, then move this one up along that, then move this one up along that. And there's a very precise way of doing that in differential geometry. When you do that on a curved surface, the result is not going to be this, right? You're doing it along a curved surface. Looking from without the surface, you're going to see something like that. From within the surface, though, you won't see this. If you live only within the surface, what you experience is a total straight line. All right? And that's exactly what they experience. At every moment, they have a straight line. Next moment, they have a straight line, straight line. It all adds up to, from our perspective, curved. Which again tells us that a theory of curvature is the appropriate one, because curvature has exactly this property. We can write a field equation. We have a field quantity, the curvature of the straightest lines in this curved spacetime, which we expect to be similar functionally to the curvature of these world lines. Right? Now, how would we find a field equation for that? Okay, I'm going to stop here for a second just to take questions if there's puzzling, because we're going to move on from this point to something, to that field equation. Let me see if there's no questions. I mean, either everything's clear or nothing's clear. So, so far so good? Good? Okay. So now we're going to look for a field equation to describe not the acceleration, not the world line curvature, but the curvature of the straightest lines in this curved spacetime. We might expect maybe that in the Newtonian regime, where Newtonian physics is correct, since the equations give the same result, that equation will look very similar to the equation that you have in Newtonian physics. Okay? We're going to start with a model of gravity, gravitational field equation, but in a more sophisticated way. And then we're going to adapt that somehow to this full-fledged theory.